All right. Chapter 4, Section 1 is on measures of location. So the entire chapter, the official title for Chapter 4 is Describing and Summarizing Data from One Variable. And we're going to go over measures of location, measures of dispersion, measures of relative position, and that includes box plots, outliers, data subsetting, analyzing group data, proportions, and percentages is the last section. And that section is like 2 pages. It's not a lot. It's just you got to make sure you know how to do proportions, work with those, and get percentages. All right, but the first section is on measures of location. So make sure that you pull out your PowerPoint because I kind of use it as a guide when I go over things. And the first thing that we're going to look at is the arithmetic mean. So the mean of a set of data is simply, it's like what we think of as the average. So the way that we find the mean of a set of data, like the official mathematical definition, is that you add up all of your data items, so ever how many you have, and after you add all those up, ever how many you have, you divide by that number. That's the arithmetic mean. The symbol that we use is this symbol here for a sample. So for a sample, we use X bar. All right, X bar, that's how you pronounce that. X bar. That is the, or a sample mean. Most of the times we're working with samples. Another way to write this formula up here is, does anybody know what this symbol is? That's an uppercase sigma, which means to find the sum. So another way to write this formula is X bar equals the sum of X divided by N. Okay? So me writing the sum of all the X's, putting pluses, or me writing this right here means the same thing. You know, not everyone has seen that before. Not everybody. I have students that come into Calculus 2 and Calculus 3. They've never seen it before. They never saw it in high school. And so they first start learning about it in calculus. Well, we use that symbol a lot in here for our formulas. And that just means the sum of X. Okay, so I would, if you need to write yourself a note so that you know every time you see this, and again, that's an uppercase sigma, it means the sum. Because there are some formulas we will use that's going to have 5 of those in it. And it'll just mean the sum of X, sum of Y, sum of, you know, X squared, things like that. So every time you see that, that means take the sum. All right, so again, what we think of as the average, in statistics, we don't call it the average. We call it the mean. All right, and if we are dealing with a sample, which in most cases you deal with samples, then the mean is X bar. All right. Now, if you look at the fourth slide in the PowerPoint, it says given some point A and a data point X, X minus A represents how far X deviates from A. So that's probably a new term as well, and we're going to use the word deviate. I'm going to use that to explain other things, but you know, in the real world, if you deviate from something, maybe you go away from something, right? If I'm walking down the street and I see something maybe that scares me, I'm going to deviate away from that. I'm going to go away from that. Well, in math, if a value deviates from another value, then that's just how far away it is, the difference that it is. Because there's a term we're going to use called the standard deviation. It's a big statistics term. And I want to make sure you understand what deviate means. We'll use it in another formula soon, so you'll get a little practice with actually what a deviation is. All right. Now, I told you what the sample mean symbol was, X bar. All right, sample mean. What about a population mean? So what if we're talking about a population, something that we can actually work with that's considered to be a population? The symbol is this symbol here. Anybody know what that symbol is? That is a lowercase mu. You probably got an email from me about mu alpha theta, or you may or may not have. Well, that's our honors math society. All right, so that's the lowercase mu. And the way you find the population mean is the same. You add all of the data items together and you divide by the total number of data items. It's the same thing. So let's say that I wanted to find the mean of the following test grades. So I had a 100, a 98, a 92, and a 50. And I wanted to find the mean of these test grades. Well, I'm simply going to take my calculator. I'm going to add all these up. So I have 4 test grades. And then I'm going to divide by the number of test grades, which I said was 4. And we'll have our average, or our mean, sample mean. All right, which is 85. So X bar, we'll call this a sample, it's going to be equal to 85. And we all know that. We know how to find our test averages. If anything, we know how to figure out an average or a mean of our test grades, because that's important to us. It's something that has meaning, right? This term, or this test grade 50 right here, that was a little different from the other test grades, wasn't it? That type of term, or that type of data item, if it's very different like that, that's called an outlier. in your PowerPoint says an outlier is a data value that is extremely different from other measurements in the data set. So that is extremely different from those other tests. It goes on to say that statistical measures which are not affected by outliers are said to be resistant. So would you think that the mean is resistant? Could the mean be affected by outliers? Yes, it can. Greatly, right? You can see by making a 50 on a test. I mean, I had an A in the class until I made that 50. And that 50 pulled me down to a mid-range B. So we can say that the mean is not resistant. I'm sorry. Yeah, because let's see, the mean is not affected, so it's not very resistant. The mean is not affected. No, the mean is affected, so it's not resistant. There are other statistical terms, types of data that we're going to look at that are resistant. Okay? That means that if the data set has an outlier, then it's really not going to affect that type of statistic that we're looking at. It's definitely not going to be the mean, though. Going back to deviations, let me show you what a deviation is. Because we said that a deviation is how far a data item is from another data item. Well, I found the mean to be 85 here. So I'm going to make a little table and show you the deviation of each data item. So this is going to be the deviations from the mean for our test grades. So these are going to be our data items, our test grades. And then this is going to be the deviations from the mean. All right, so we had a 100, we had a 98, we had a 92, and we had a 50. Now, our mean was what? 85. So, if I take and I say 100 minus 85, the deviation from the mean would be 15 points for 100. Okay. If I take my 98 and subtract 85, the deviation from the mean would be 13. 92 minus 85, the deviation from the mean is what? 7. And then if I take 50 minus 85, the deviation from the mean is negative what? 35. So the deviations can be negative. Now, what do you think would happen if I took the sum of the deviations? So I'm going to take the sum of the deviations from the mean. That would be 15 plus 13 plus 7 minus 35. (15 plus 13 plus 7 minus 35). We get what? 0. Okay, and so that happens. It has to happen for us to have that as the mean, 85 as the mean. And I sum up my deviations. They have to be equal to 0 there. Or do they? They have to be. All right. Now we have something called a trimmed mean. And if you look at the bottom of the second page of your PowerPoint, you'll see it says the trimmed mean is a modification of the arithmetic mean, which ignores an equal percentage of the highest and lowest data values in calculating the mean. So what the trim mean is, it's a way to find a mean that could possibly get rid of outliers. Now, outliers are not always bad, right? If I have a bunch of low test scores and then I have one high test score, then the high test score is the outlier. So, I mean, the high test score for me would be good because I would be happy I made that. But if I find a trim mean, what the trim mean does is it takes a percentage of the top and bottom away and then finds the mean of everything that's left over. It trims off the ends, the high values and the low values, and gives you, I guess, if you had outliers, it would give you a better representation of the data. Okay, so it kind of gets rid of the outliers. So for example, if you look at your next PowerPoint, page 3 in 4.1, they work through a problem finding the trim mean. So let's read through that problem and figure out how they got their answer. So look at the data set there. This is on page 3 at the top right hand corner. And so they took this set of data and they found the mean to be 25.5. This is a poll taken from how many text messages a person sent in a day. Some of you have probably sent this many during class. Hopefully not. But that's the mean. Well, find the 10% trimmed mean. So what we want to do is we want to see what 10% of the data items would be. So how many data items are there here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what is 10% of 10? That's 0.1 times 10, or 1. So what I want to do is I want to take off the top, since I got a 1, I want to take off the very lowest value, and I want to take off the highest value. Okay, and this will give me a 10% trimmed mean. So now I add these 8 data items together. I'm going to say 18 plus 20 plus 21 plus 23 plus 23 plus 24 plus 32 plus 36. And then what do I have to divide by? 8. Okay? Because there's 8 data items. And if you look at the next PowerPoint, you can see they got 24.625 whenever they divided. The next slide says if there would have been 100 data items, if there would have been 100, and we did a 10% trim mean, then that would be 10. So you take off the 10 largest and 10 smallest. What about a 20% mean if it would have been 100? You take off the 20 largest and the 20 smallest. Again, why find a trim mean? Because since the mean is not very resistant, finding a trim mean can get rid of those outliers. Okay. So the trim mean is a resistant measure. All right. Next, the median. All right, so to find the median, you do have to arrange the data items in ascending order. So it will be first, I guess you could say, to find the median, first arrange the data items in ascending order. All right. Then the median is the middle data item. If the number of data items is odd. So after you arrange the data items, if you have an odd number of data items, then of course there will be a middle number. If the number of data items is even, take the mean of the 2 middle items, or middle data items. So median is middle. Your PowerPoint, I didn't really go through these steps, but I just kind of put it all together. It says arrange the data items in ascending order, determine the number of values in the data, find the data value in the middle of the data set. If the number of data items is odd, then the median is the data value that is exactly in the middle of the data set. If the data value is even, then the median is the mean of the 2 middle observations. So let's just take that same data set up here. I'm just going to copy it again and paste it again. All right. What if I want to find the median here? Okay. Well, there's 10 data items. So there's not a data item exactly in the middle. And this is already arranged. So these are already arranged in ascending order. So we have 2 middle data items here. So I got to say 23 plus 23 divided by 2. which really I don't have to say that because I know 23 plus 23 divided by 2 is equal to what? 23. And the mean of two numbers that are the same is just that number. So anybody ever wonder what the median is when you're driving? Stay off the median. Median's the middle, right? See that on the interstate? They don't want you driving up there in the middle. All right, but what if we have an odd number of data items? So, for example, because an odd number of data items, it's going to be a little bit easier. Let's find the mean of this set of data. So what's the first? Can I just go to the middle? There's 4. Well, actually, this is an even number again. Can I just go and do that and get those two? No. What do I have to do first? I have to sort them, right? If you don't sort them, you can't find the median. So it'll be 65, 72, 76, 83, 85, 88, 90, 94, 98. Now the two middle items are there. 83 plus 85 divided by 2. It's going to be 84. So that's the median. Let me find you one with an odd number of data items, because that's the easier one. So let's say that I had this set of data, and it's already going to be sorted. So just to show you how much easier it is, once you sort it, you look for that middle term. Oh, it's kind of blurry. You see you got 5 here. Oop. You got 5 here, and you have 5 here. So it's exactly in the middle. So that's the median. Is the median a resistant term? Is it a resistant item? So is it affected by outliers? It's not affected by outliers. So that means it's resistant. So like if this set of data, if I would have had a 1,000 right here, I mean, it may change the median. In this case, it wouldn't, right? Because then I'd have two middle terms. So outliers do not change the median, so the median is a resistant term. All right, next let's look at the mode. The mode is simply the data item that occurs the most frequently. Most frequently occurring data item. All right, so you can have no mode if no data items repeat. You can have two modes. That means it's bimodal. Or if we have 3 or more modes, we don't say trimodal, we say it's multimodal. Okay? So let's look at this data up here. What's the mode? Yeah, right, there's 3 3s. So the mode equals 3 for that set of data. Again, if you have the same number of data items for 2 different data items, then you can have 2 modes. You can have 3 modes. You can have 4 modes. You can have no mode. So like our test grades up here that we were looking at, there we are, those 4 test grades, no mode. Because none of the test grades repeat. The last term that is explained, this is something kind of new to me, a moving average. It says a moving average is obtained by adding consecutive observations for a number of periods and dividing the result by the number of periods included in the average. So I doubt you'll see that again. All right, the next section is on measures of dispersion. All right, I've already showed you what a deviation is. I'm going to read a little bit out of the book to try to explain a little more what measures of dispersion are. Suppose all people looked alike. All cars looked alike, everyone wore the same kind of clothes, and there was only one kind of hamburger, which was plain. That would be pretty bad, right? Without diversity, it would be a boring world and a world in which statistics would be of little value. Since much of statistics is devoted to describing, analyzing, and explaining variability, that means that, how things vary. It would be pretty boring if nothing varied, right? The concept of variability, also referred to as dispersion or spread, is as vague as the concept of central tendency. And vague concepts lead to different measurement ideas. The same issues that are important in evaluating location measures are meaningful in evaluating measures of dispersion. Many of the good measures of dispersion use the concept of deviation from the mean. That's very important. If the mean is a focal point or base, use it as a common basis from which to measure variation. The distance from a point, or the distance that a point is from the mean, is called deviation from the mean. All right, and I've already showed you in a table. Here's another table that shows you, and let's see if it's in your PowerPoint real quick. This exact table is not, but I'm going to show you just another table that shows deviations from the mean. So how would I calculate deviations from the mean? I would have to know the mean, of course. Then I would take the data item, and I would say the data item minus the mean. That gives me the deviation from the mean. It's the distance that data item is from the mean. Like if you think about a number line, and on that number line you know where the mean is, and that number line contains all of our data items, then it's kind of like the distance from the mean. Whether it's a positive or a negative, it's still a distance away, either to the right or to the left on the number line. All right, so you can see the deviation from the mean for 3 is 3 minus 10. The deviation for the mean for 12 is 12 minus 10, and so on and so forth. All right, notice if I sum all of these up, what I get? I get 0. All right, so we're going to use that fact to figure out something called the mean absolute deviation. But before we do that, the book introduces one more term. We're all pretty familiar with the word range, but it's not in the same maths. This isn't the range that usually goes with the dependent variable y. I'm not talking about that. In statistics, the range is kind of like how big the spread is of the data items. So to find the range, you say the largest data item minus the smallest data item. And remember, if the smallest data item is negative, you're subtracting a negative, so you would have to add it. Okay? It's the largest minus the smallest. Real easy to find. Like if I wanted to find the range of these data items here, what's the largest? 20. What's the smallest? 0. The range is 20. All right, now the mean absolute deviation. And we're going to have to use something like this whenever we go over another type of deviation that's very important to statistics. All right, the mean absolute deviation, or simply MAD, you mad? Hopefully not, is equal to the summation of x sub I minus x bar, the absolute value of that, all over n. X sub I simply stands for any data item, or every, this in this summation means we do it for every data item. So x sub I will be every data item, like x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, where each one of those would represent or stand for a data item. I'm not trying, let's not try to make this any more complex than it is. But let's say that we had this set of data. Let's see, my x values were, I'm going to make a table, small table here. Let's say my data items were, and I believe this is in your notes, so we'll do it. It's in your PowerPoint. 5, 10, 9, 11, 9, and 7. Okay? Then the deviations, we have to know the mean of that set of data to find the mean absolute deviation. So we add all those up and we divide by 6. All right, and we have to know the mean to be able to find the mean absolute deviation. We get x bar is 8.5. All right, so now I'm going to make a column here of x sub I minus x bar. Okay, so that's going to be 5 minus 8.5, and I want to actually be able to find an answer, so I'm going to make that a little bit bigger. 10 minus 8.5, 9 minus 8.5, 11 minus 8.5, 9 minus 8.5, and 7 minus 8.5. All right, so if I do all of those, let's see, I get negative 3.5, negative 1.5, and this probably isn't in your table, but I'm going to write all these down. 1.5. Wait, no, that's 0.5, right? Oh, it's positive, sorry. I don't know where my brain is. All right, yeah. What is the next one? What's this one? 3 or 2? 2.5. What's this one? 0.5, and what's this one? Negative 1.5. All right, so we know if we add all those up, we get 0. But that's not what we're doing here. So what we're doing is we're going to take the absolute value of x sub I minus x bar. So that just simply means that we make all of the answers that we got positive. So that'll be 3.5, and I'm doing my table a little bit different. I wrote my negatives here because I wanted you to see. I'm making another column now, and I'm finding the absolute value of that. So it's 3.5, 1.5, 0.5, 2.5, 0.5, and positive 1.5. It's absolute value, so it's all positive. So again, let me go back. I know earlier I showed you that the sum of all the deviations equals 0, and it does. If you add up all those answers in that second column, since you have positive and negative answers, you would get 0. All right? However, with the mean absolute deviation, what we're doing is we're finding the absolute value of the deviations. And now I need to find the sum of the absolute value of those deviations. So what I like to do, if I make a table like this, and it's, it's near the bottom, so it's not of the page, it's not very good. But I'll usually just say sum, since I need that in my formula up here, equals, and I add all those up. Okay? So when you add all those up, you get 10.0. So our mean absolute deviation is 10.0 divided by the total number of data items. How many data items do we have? 6. All right. And so that's going to be 10 divided by 6. I'm going to round one more place than the data items have. The data items have no decimal. They have a decimal place of, it's 0.0, right? So I'm going to round to one place. So that will be 1.67. Or no, if I round to one place, it would be 1.7, sorry. It's always important that we look at the directions and see how many places they want. But in general, just if you look at other textbooks, we'll usually do one more place than the data set has. So that's the mean absolute deviation. All right, so what does that mean? On average, the data items are 1.7 units from the mean. And I have to use the word average there. On average, the data items are 1.7 units from the mean. Oh yeah, how many units from the mean? It's 5. Yeah, it's negative 3.5, but as a distance, it's 3.5 units. It's just to the left on the number line, right? And how many units is 10 away from the mean? Well, it's 1.5 units away from the mean. But on average, the entire data set, altogether, on average, it's 1.7 units away from the mean. Now, do you think the mean absolute deviation is very resistant? Well, what if I was to put like a data value up here of 100? What would that change? Would that change the mean of the data set drastically? Yes. So then I would be subtracting by some bigger number, maybe like 30 something. And then that would change these values. So then that would be a lot bigger. So then I would say a lot bigger divided by 7 because I have another data item. And that would mean my mean absolute deviation would be bigger. So that just means that the mean absolute deviation is not very resistant either. Okay, it's not a resistant term. But we do use that same concept to go over probably the most important term that we're going to cover so far in statistics, and the one that usually is the first thing that gives students trouble in statistics. And that is the variance and the standard deviation. This is like a very big, important, so if you need to send a Snapchat, go ahead and do it right now so that you can pay attention to what I'm about to show you on the variance and the standard deviation. We use we're going to use all this other stuff too for the rest of the semester, like the mean and
sometimes the median, probably not the mode that much, but we will use standard deviation for the rest of the semester. There's only a couple of topics that we cover that don't have standard deviation. And variance. All right, so we all know we're going to have a population version of this, and we're going to have a sample version of this. Because that's just, if we're talking about an entire population of something, we use one variable. If we're talking about a sample version of this, we use another variable. But they're called the same things, they just look different. Okay? The first thing we're going to go over is the variance. Okay? The variance is, this is a lowercase sigma. It kind of looks like a O. Mine I flatten out the left side and I shouldn't. It kind of looks like a O, but then it has this little mark that comes over. Okay? So that is a lowercase sigma squared. And that is variance. That is population variance. Now I'm going to go over the symbols before I go over the actual formulas. And that's a L, not a T. I don't know why I crossed it. All right. The sample variance is S squared. All right. The population standard deviation is just sigma. That's population standard deviation. And the sample standard deviation is simply S. All right. So now, mathematically, what would we have to do to change sigma squared into sigma? What mathematical operation would we have to do to change a variable squared into a variable to the first power? Take the square root, right? So that is the relationship between these two terms. The square root of the variance, whether it's population or sample, is equal to the standard deviation. That's probably one of the most important statements that I've made so far in this class. The square root of the variance is the standard deviation. So it is so, if we're just talking about it, and even the symbols are like that. Okay? Sigma squared is population variance. Take the square root of that, you have population standard deviation. S squared is sample variance. Take the square root of that, you have S. That's sample standard deviation. It is important that you remember that. You have to commit that to memory. You have to learn that. Because From now on, we're going to be working problems, and some of them require us not only to calculate this, and I'll show you the formulas, but they require us to use this to do other stuff. And some of the problems are going to give us variance, and we need standard deviation. So we have to take the square root of it. Or some problems that give us a standard deviation, and we want to use standard deviation, so we don't have to do anything to it because we have it. So we need to just understand the square root of the variance is the standard deviation. I made a big deal about it because it is a big deal. Kind of like myself. All right. Just kidding. So what about our formulas? How do we find this stuff? Okay. So it's for population variance. Population variance is equal to, and there are several formulas for this. We're just going to go with the one that the book uses, okay? Because there's different ways to calculate it. It's equal to the sum of x sub I minus mu squared divided by capital N. Now, this is a population, so it makes sense that you have a population mean here. This just stands for every data item, x sub I, and the capital N stands for the number in the entire population. All right, if we're talking about a sample variance, S squared is equal to the summation of x sub I minus x bar squared, all divided by n minus 1. Now, you should be thinking, why n minus 1? Why not just n? So, when we divide by n minus 1, I don't know if this is in your PowerPoint or not. So, I don't see it. So, when we divide by n minus 1, it will give us an unbiased estimate of the population variance. So we get an unbiased estimate of the population variance. So if we calculate the variance, either the population variance or the sample variance, how do you think we get the standard deviation? We take the square root of it. So if we use a formula and we find the population variance or the sample variance, and we need the standard deviation, we simply just take the square root of the population variance or the square root of the sample variance. Now this does take us to, or this does take a little time to do. All right. So if we took that same data set that we had earlier, the one where we had 5, 10, 9, 11, and I'm going to copy some of this down from where I've already worked it out. And then we had what? We had the deviations, x sub I minus x bar. So let me do that. And we had the mean was 8.5, right? So I'll write down how I get this answer. It's 8 minus 8.5. We got that as negative 3.5. And then we had 10 minus 8.5, and that was 1.5. 9 minus 8.5, 0.5. 11 minus 8.5, that was what? Was that 2.5? And then 9 minus 8.5, that was 0.5. And 7 minus 8.5, and that was negative 1.5. All right, so we've already done that. What we haven't done is we haven't taken the difference here and squared it. So if we take each deviation and square it, what would we get? So we want to say negative 3.5 squared. When we do that in the calculator, we get 12.25. Then we want to say 1.5 squared. That gives us 2.25. Then 0.5 squared. That gives us 0.25. Then 2.5 squared. That gives us 6.25. And again, 0.5 squared is 0.25. And negative 1.5 squared is, again, or 1.5 was 2.25. Are all of those answers positive or negative? They're all positive, right? So when you square data items, or you square the deviations there, we always get positive values. Okay? Always get positive values. So what if I wanted to know the sum of these deviations squared? Well, then I have to add all these numbers up. So if I add all these numbers up, I get 23.5 if I do that in a calculator. So this came from a sample, so I'm finding the sample variance here. So the sample variance, remember the formula was the sum of x bar minus x bar squared. We got that as 23.5, and that's divided by n minus 1. How many data items are there? 6. So 6 minus 1 is 5. So 23.5 divided by 5. So I know that my variance is 4.7. So that is the variance, the sample variance. What if I want the sample standard deviation? I have to take that and find the square root of that. Now I'm going to round this to one place. What would it be? 2.2. So my population variance is 4.7. Not population, I'm sorry. My sample variance is 4.7. My sample standard deviation is 2.2. Okay. Standard deviation takes some practice. Variance takes practice.